Okay, now we are for like in the last question of the midterm exam, and I also thought this is super simple question, but I see a lot of math in your answers. So let me show you what's going on. So, so the first question is to check exogenaity assumption, and the second question is to check the relevance assumption. Uh, First, about the exogenaity assumption, I thought it's still I think it's clear. I could not be more clear in the question. Just exogenaity assumption. We have mentioned it many times in class, and let me clarify uh, the definition. So exogenaity assumption means three different can mean three different things depending on the context and the models. The first, the most mild assumption is the uncorrelatedness. Simply x and epsilon are uncorrelated. And the second assumption is mean independence assumption, which is the conditional mean is zero. Conditional mean is zero. And the second assumption implies the first one. So second assumption is a stronger assumption, which is less desirable, right? My assumption should be mild and more general. So the second assumption is more strong, and the first assumption is more mild. And the third assumption is independence, which means epsilon and x are totally independent. And they have strict relationship. 3 is the strongest. 3 implies 2, then 2 implies 1. So 1 is mild, 3 is strong. 3 is the worst among them. If you can use assumption number 1, then you have to use this, not number 3, right? So then, however, in the linear model we consider in this class, we only need the uncorrelatedness. Everything is linear, so the model is pretty simple. Everything is simple, so uncorrelatedness is enough. However, later, if you make your model more complicated, and then you may need number 2 or number 3 for more complicated model. You need more information to identify the complicated model, so you have to make a stronger assumption. That is, so in that sense, you may interpret this as an exogenaity assumption or this as an exogenaity assumption, but we have not considered them yet. In this class, our definition was number 1. But the problem is some of you are just showing number 2 and did not mention anything about number 1, or started from number 1 but just proved number 2, and you have to show that number 2 proves number 1. So I don't know, even within your answer, it's not consistent. So the starting point and the end point are different, and then answer is suddenly finished. So to clarify that, so if you, I don't know why, but maybe if you wanted to use number 2 as the exogenate assumption, you have to declare that. I understand. Then I would take your answer as a reasonable, correct answer. But without saying anything, just showing number 2 is a problem. Then using different definition and something is not complete, right? That's what I wanted to say. Otherwise, proof is pretty straightforward. And part B. In part B, I'm asking you to show relevance assumption, which I think is also very clear. And the relevance assumption in general vector case is the rank condition. Rank of this guy should be the same as the dimension of x. So we assume x has dimension of k, so the rank should be k if both x and z are vectors. And in our case, in the question, you may simply consider covariance non-zero. I think we did it in a homework, And we could do this because even though there are two variables, intercept and x, but intercept does not matter much, but because there is an intercept and both are other than intercept, all the variables are scalar, so you may simply consider covariance. Then showing this is also not that difficult, but let's see. I'm going to show you some problems in your notation. What matters more is your notation, not the proof. The conclusion is clear. You know what to do. But the process going there is a totally mess. So let me start from very simple example of function, the notation of a function and not a function, constant. Function and constant are different. So think about case number one. Fx equals to x squared. Obviously, this is a function, which means if you input x, then your output is x squared. So if you put a different value, you are going to get a different output. That is function, right? And now consider its derivative. Derivative of this is also a function because the slope can be different at different points. If you choose a point x, then the slope is the tangent line, which can be different where you are depending on the value of x. So it is a function. Different points give you different slopes. So you have the degree of freedom of choosing x. However, now consider integration. You may think integration is the opposite operation of differentiation. That is right, but the major difference here is this differentiation, like integration, is not a function. Integrated function is not a function because it's just a number. You can calculate that. Integration is 1/3. The area between 0 and 1 below the function is 1/3. There is no argument. The area does not change depending on x because x is integrated out. You have to consider all the possible x at the same time between 0 and 1 and calculate kind of some of them, some of the areas below the function on that interval. So in that sense, it is a number. It does not depend on x, and you have no choice, right? You cannot choose what is x in the integration. So in here, x is integrated out. And it is not a function of x anymore. It is just an integration. It is just a constant. It is a number, right? You cannot choose anything, right? So I want you to distinguish what is a function, what is not a function. Next, think about CDF, cumulative distribution function for a random variable. It's a function because if you choose a point, it will calculate the probability smaller than or equal to that point. So if you choose a different point, the answer will be different. So that is a function. It is a mapping. Obvious. Then now think about expectation. Is it a function? No. Because it's an integration. Same reason. You integrate it out. All the possible value of x is already considered. So already you have to use all the possible outcomes for x to calculate the expectation. And then in the end, you have no choice. All the values are considered. It is just one number. Expectation can be 0 or 1, not a function, right? So it's not a function. Then, now consider conditional CDF. F of y given x. It is a function of both x and y because it changes depending on x. So if it does not change, that means x and y are independent. But in general, if you choose a different point of x, the distribution of y may be different. So it's a function of x, it depends on x. And also, for the same reason as here, depending on what you choose, the y may give different answers. So it's a function of both arguments, x and y, right? And number 7, conditional expectation. Is it a function? Yes, but it's a function of x only. It's not a function of y at all, because look at this. It's an integration, but it is integrated only with respect to y. Y is integrated out, but x is not. If you change x, the conditional PDF will change, so your conditional expectation will change. So if you choose a different x, your conditional expectation will be different. So it is a function of x. And then, so then you like, sometimes we write it this way. So this means we are fixing x at a certain point x. So then it is just a one evaluation of, it's a function of x, but at the same time, we, like as I did, we may write it this way. Then you can think it as a random variable, a function of random variable x. So if random variable x, then you can think about its squared or some function of the random variable. The function of random variable is still random because the random variable is random. Then it is random. The conditional expectation of y given x is random because x is random. It's because of x, not because of y. Y is integrated out. Randomness in y is integrated out, does not exist anymore, but randomness in x still remains in here. So this is random. You have to understand that. And then now, another dimension, probability measure. Let's think about probability measure. Probability measure is a function that assigns a probability to each measurable set. Measurable set on real number. I'm not going to define what is a measurable set, but so for any interval, you can think about its probability on the interval. So as you see, it's a function defined on an interval, for example. So you can think it this way. However, so that means what I wanted to show you here is this is a function, which is a function, but its argument is an interval, not just a number. So for example, in this function, it is not defined at all. In this function, you cannot use an interval as an input. If you think about f of an interval, makes no sense. It's not defined. The domain is totally different. Domain of the function f is real number, not an interval of the real number. Then what is this? What does it mean? I have no idea. It does not make any sense. Well, I don't know why equals to 1 stays inside the expectation. Then is it, of course, expectation of x times y is not a function at all. No, it's not a function at all. Then does it make sense? If x equals to 0, expectation of x times y equals to 0. Makes no sense because x does not change this guy at all. This is just a different constant. Just a different constant, independent constant, regardless of x, right? So even if, no matter what x takes, it does not change. So that's the problem. Then let me look at your answers. I don't know what this means. So left-hand side is the same. I don't know why suddenly the 0 and 1 are included, and I don't know why suddenly they equal to 0 again. I don't know what this guy wanted to say here. Have no idea. I don't know. It's anyhow the equalities totally fail. And let me see. I have seen a lot of notational digesters. I have no idea. So same thing again. When z equals to 1, it does not depend on z. Something is not right. It's not a function of z, then no matter what z is, it should be the same. When z equals to 1, when z equals to 0, does not matter. Expectation does not depend on z, right? Mathematically wrong. Totally wrong. So this is wrong. First of all, expectation conditional on z. It's conditional on z, but suddenly it goes to expectation of z. Mathematically, this is wrong. This is wrong. And second, this is wrong. We do not have, it's not defined at all. Expectation of z equals to 1. I don't know what he wanted to say here. If z equals to 1, this should be 1, not p0. So I have no idea what notation, like what this means. Same thing again, not defined. And others are, I think. Good job. So here in the last question, it's simple. So I think it's a very introductory statistics. It uses only introductory statistics to like such as the iterated low iterated expectations, and just simple algebra and showing exogeneity and relevance conditions, which I think pretty straightforward. But I was kind of shocked. Make no sense in terms of notation. So think more carefully when you write down what you are saying. So as I said in the earlier video, it's like you are saying, I am going student. I don't know what you wanted to say. Just there is nothing like that. Or I feel like I'm not sure if you're talking in English or like you are talking in statistics. It's not the language of statistics. That kind of meaning sentence does not exist. So it was hard to fix what's wrong. So it's totally wrong from the very beginning, from the very fundamental. And by the way, another thing. You are in this question, you have to show exogeneity and relevance assumptions. And these assumptions do not depend on which approach you take. Like even if you use the fitted value approach, the proof does not change because, so think about what comes first. Relevance assumption is the first thing you have to settle down, and then you take fitted value approach, or you choose which approach you use. So for example, if you set up this equation, and then what you need to show is delta equals to delta does not equal to 0. And to do this, you have to show this. And showing this does not require this functional form. And so you have to show this. And then it's more complicated. You have to show that the numerator is not 0, denominator is not 0. And in the end, the denominator is not 0, as like when the numerator is not 0. So in the end, it does not do anything. The functional form, the regression equation, does not do anything in this proof. In the end, what you have to prove is this. So you don't need to set this up. And setting this equation is not wrong, but if you utilize this equation in showing this, something is wrong. Something is not going right? So you need this assumption to define it this way. But if you to show this, you cannot use the equation. So hope it helps. And by the way, don't worry about the grade. Just worry about your understanding, your learning. So, and if you have any questions, I'll be happy to help you. but it's mostly not what I taught. The main problem is coming from the very fundamental statistical notation and concepts. What if it's a function of something, or if it's random, or something like that, right? So, and what you have to learn from this course and like from this exercise is to make a logical argument uh, based on statistical knowledge, based on the assumptions, and from the assumptions you have to prove the next statement, and then you get like step by step. So that's what you have to learn here. And of course, yeah, it's not easy, but it takes time. But still, you have to practice. This is PhD life, so you have to think more logically, more rigorously. So hope it helps. See you later.